Welcome back to the lecture series on microeconomics. Today we are going to have a discussion on optimization theory and some of the associated techniques. Whatever we have discussed so far, it is quite evident that all economic agents are optimizers. Now we are going to move on to the case of two variable optimization. Of course, this can be generalized to n dimension, n number of variables, but let us not get into the complications. This is not a advanced level microeconomic theory course. For this course, if we know up to this, that would be good enough. So, in the case of two variable optimization, let us start with this maximization problem. A function defined over two independent variables x1 and x2, these are the decision variables. So, my maximization will be with respect to x1 and x2. So, what will be the first order condition? In this case, first order condition will be the partial derivative of the objective function with respect to the decision variables, we need to set them to 0. Now, the second order condition is a bit complicated compared to the first case. Here we have to introduce a concept called Hessian matrix. The second order condition is represented through a Hessian matrix. Now, the Hessian matrix is defined as H F11, F12, F21 and F22. So, these are all partial derivatives, right. So, in general one can write this Fij is this partial derivative. Now, again there can be two types of problems, one maximization and one minimization. So, we have started with the maximization problem. So, let us look at the second order condition for the maximization case. For maximization problem, the Hessian matrix must be negative semi definite. Now, what do I mean by this new term that is introduced here, negative semi definite? Those who are doing college level matrix algebra may be aware of this concept. Those who are not, for them let me define this very quickly. So, let us assume A to be a n cross n symmetric matrix and a K to be the K cross K submatrix. So, this is basically the upper left hand K cross K submatrix of original matrix A. Then let us also define determinant a k, the definition of determinant should be known to you, then A is negative semi definite if is positive for k taking values 1, 2 up to n minus 1, and determinant A should be 0. Now, if we are dealing with a minimization problem, then what will be the shape of the second order condition? Again we have to construct the Hessian, of course, and then this is the result that I am going to state. H matrix must be a positive semi definite one. What do I mean by positive semi definite? So, let us stick to that same definition of A, and then A is positive semi definite if determinant A k is positive for k equal to 1 to 2 to up to n minus 1, and determinant A should be equal to 0. Now, in this case let us look at comparative static analysis. So, now we are going to discuss a two variable maximization problem. So, we will start with the first order conditions, and then we are going to see how from there we can conduct our comparative statics analysis. So, we will start from the first order condition directly. I said that I can assume that the decision variables are basically the functions of the parameters. So, I am writing explicitly as I did earlier also. So, this is say equation number 1, then I have del f So, I am differentiating the same function this time with respect to my second decision variable, which is x2, and I am setting that equal to 0, and these 1, 2 equations, they will give me the first order conditions. Now, for a comparative static analysis, differentiate one with respect to the alpha, the parameter, and that will give you f11 del x1 del alpha plus f12 del x2 del alpha plus f1 alpha, and that would be equal to 0. Now differentiate 2 with respect to the parameter alpha, which is changing, and now we will get f21 del x1 del alpha and you need to set that equal to 0 as well. So you get two equations and you can name them number 3, number 4. What are the variables in these equations? We are actually interested in the comparative static components, which are namely del x1 del alpha and del x2 del alpha. So these are the variables of interest. We have been discussing the role of optimization techniques in economic analysis. Now we are going to continue with what we have learned so far. We are going to see an example of optimization exercise in microeconomics. We are going to go back to the discussion on the Marshallian consumer analysis. We have already seen how in a Marshallian world consumer optimizes. Now we are going to start from there and we are going to extend that to a too good model. In Marshallian consumer analysis, we have made couple of assumptions. I suggest you go back to the previous lectures and have a look at them. So I am not repeating these assumptions. So what we have done there, we have just worked with one consumption good, namely x1, and then we said that the consumer derives utility, which is a function of the x1 consumption only, and there is a concept called net utility, say it is denoted by V, and that is basically E of x1 minus lambda P1 x1. So if you remember the discussion we had earlier, so in the one variable model, this is the gain of the consumer and this in terms of the utility, and this is the loss of the consumer in terms of utility as well. So a consumer maximizes net utility U of x1 minus lambda P1 x1. We have looked at the first order condition and all, and of course the decision variable has been x1 there. Now we do not want to get into the first order condition. Let us look at the graph. so that we can get some insight into it. So I am plotting U along the vertical axis and quantities or units consumed of commodity 1 along the horizontal axis. Now utility is a concave to origin function because of the law of diminishing marginal utility, and let us see how the consumer actually optimizes in this given setup. So, as the consumer consumes 0 unit, then of course there is no loss, but as the consumer started consuming positive units, the positive units will be multiplied by the price of the unit and the marginal utility of money. And of course, this lambda 1, lambda p1 that you see here will be a constant. So, we are talking about basically a positively sloping, upward sloping straight line. And let us draw such a straight line, and this can be lambda p1 x1. So, you can see the area that the consumer that the area which gives the consumer's net utility is given by this dashed area, and the net utility is maximized when you have a straight line drawn as parallel to this lambda p1 x1 straight line and the point of tangency of that line to the utility function. So, that tangency point, at that tangency point, the gap between this straight line lambda p1 x1 which is the loss function and u of x1 which is the gain function is highest, and that is why at this point the utility is maximized, and we can say that we have obtained the optimized value of x1 star. So, this is where we have stopped. No, not really, because we have then talked about the first order condition also, and then we have derived the first order condition to be marginal utility of commodity 1 divided by the price of commodity 1, and that was equal to the marginal utility of money lambda. Now, up to here we have started. Now, let us think about an extension of the model. To do that, we have to have some more assumptions. Number 1, we assume different utilities are independent. By that we mean that when the consumer derives utility from consumption of x1, it does not depend upon the quantity of consumption of commodity 2. We also assume that utility function is additively separable. What do I mean by that? I am going to show you right now. So, now we are going to start with the new utility function u this has two components, u of x1 plus u of x2. So, you see the utility consumed from consumption good 1 and utility consumed from consumption good 2, they are independent. Now, if we start with that utility function, how would the consumer's maximization problem would look like? So, we can talk about a net utility function V remember we have to extract the loss also. So, here comes the loss, this is the expenditure on commodity 1, this is the expenditure on commodity 2, and you multiply that with the marginal utility of money. So, this gives you the loss, and of course, the decision variables are x1 and x2 in this case. So, in this case you can very well see it is very difficult to draw a graph, as you know we have two different variables consumption goods here. So, we will try to solve this optimization exercise using calculus, and to start with we have to write down the first order conditions for maximization. So, we have to partially differentiate with respect to the good 1, that will give us one first order condition, and at optimal this is going to be equal to 0. We have to differentiate with respect to the commodity 2, and at optimum this is going to hold. So, these are basically my necessary first order conditions. Now, what is the second order condition? For second order condition, you remember that we have to focus on Hessian matrix, and we define Hessian matrix H in this case as now. Let us try to interpret something more out of these two first order conditions, because we have two goods now. Note, we can write from these first order conditions the following stuff. And this is known as law of equimarginal utility. So, if you have n number of commodities, of course, you will be having more components. Now, how to interpret this law of equimarginal utility? So, if you have some amount of money, you are thinking to allocate this amount of money between two goods x1 and x2, how to split the money into consumption of x1 and x2 such that your utility is highest possible. The rule is the following. So, if you are spending say 1 rupee on x1, it should give you the same level of utility if you decide to spend the same amount of money on good 2. So, that is basically the law of equi-marginal utility. Now, let us look at the following comparative static analysis. In this case, in this model, the parameters are P1 and P2. So, these are the market prices of these consumption goods 1 and 2 respectively. So, of course, as P1 and P2 changes, the demand for x1, x2 shall change, and this is what we are going to capture through the comparative static analysis. Let us talk about this exercise, how x1 star changes when P1 changes. So, in symbolic sense, we are looking for remember this component or this derivative. Can you identify this derivative with what we have already studied? This is the slope of what we call a Marshallian demand function. So, now you can realize that one of the beautiful example of usefulness of comparative static analysis is to find out the slope of the demand function. Now, let us start from the first order condition itself. So, we have two equations there, and then the sign of this thing which is important to us can be given by 1 0 0 How we can get this done? You have two different equations there, and you have to differentiate these two equations with respect to the parameter which is changing. Here it is P1, and then you will get a set of equations, and then from that set of equations you have to apply the Cramer's rule to get the expression of del x1 del P1, and that expression, the sign of that expression actually is the sign of this particular determinant, and we can say that this is going to be less than or equal to 0. How come? Because of an assumption that we made regarding this component. So, we have assumed the utility function to be concave, and that is due to the law of diminishing marginal utility. Hence, as the second order derivative is negative, the sign is definitely less than or equal to 0. Now, let us look at the second order condition of this maximization exercise. So, we have to write down the Hessian, and that is going to be u double prime 1 x star 1 0 0 So, for the maximization, H must be a negative semi definite matrix, right, and that means u double prime 1 x 1 star and u double prime 2 x 2 star shall both be non positive. It implies less than equal to 0. So, you can see the assumptions that we make in the case of Marshallian utility analysis or Marshallian demand analysis, how that is playing a very critical role to establish that we have a downward sloping demand function and we have the maximized utility achieved for a consumer. Now, let us go back to the first order condition. Say let us call this to be equation 1, this to be equation 2. Now, this u prime component here, that is the marginal utility of commodity 1, and this component here is the marginal utility of commodity 2. Now, note we got u prime 1, say I denote this to be the ith good known as the generalized case, it can take value 1 2. We can have greater than and we can also have the case of less than. Let me start with the inequality. So, this is the first expression for first group good, and then we have this expression for good 2. If equality is not met, then what will happen? First case would be the case of this. So, u prime 1 divided by p 1 is greater than u prime 2 divided by p 2. So, in that case we can very well see that the marginal utility from commodity 1 is much higher compared to the utility gained from the commodity 2. So, in that case the consumption of good 1 should increase and consumption of good 2 shall decrease. If the reverse is assumed, and that is basically the second case, then what will happen? Then we can see that as the utility from commodity 2 is higher compared to the utility coming from commodity 1, in that case the reallocation should be such that the consumption of x 2 shall increase and consumption of x 1 shall decrease. Now, this is in a nutshell all about Marshallian consumer demand analysis, but you can probably see that there are some lapses or some limitations in Marshallian consumer demand analysis. There are some very strict assumptions. Take the case of assumption that different utilities are independent. So, this very assumption of additively separable utility function, that is absurd. Think about the consumption of a cup of tea. you have a cup of tea, then you have some sugar, you have some milk, and there is an optimum proportion of tea, sugar and milk will give you the highest utility. So it's very difficult to assume that utility coming out of one consumption good does not depend on the level of the consumption of the other good. The another strict assumption is the constant marginal utility of money. In reality these assumptions do not take place. That is why in the 20th century Marshallian demand analysis was heavily challenged, and we get a new stream of theory known as Hicks-Allen indifference curve theory. This is the modern approach to consumer behavior. In this course we are going to study that, and we are going to continue with this discussion.